Hello, everyone. In this lesson, we're going to introduce antiderivative, and we're going to go over some examples of how to find antiderivative. All right, so let's go the definition. Okay, a function capital F is called an antiderivative of f on an interval I if the capital F is being taken derivative, first order derivative, equals to the lowercase f of x for all of the x in that interval. And we say capital F of x is the antiderivative of the lowercase f of x. Theorem. Okay, if f is an antiderivative of lowercase f, capital F is an antiderivative of lowercase f on an interval I, then the most general antiderivative of the lowercase f on I is capital F of x plus a constant c. C is any constant. Okay, C can be any constant. Any constant would be okay. All right, so let's apply this concept. Okay, let's apply this concept. We can read out. So I would like you guys to practice applying this definition. For example, in the past, we've been studying derivative, right? We know derivative of a constant equals to 0. Okay, let me use a capital C. Actually, I like capital C. If a capital C is taken derivative, it equals to 0. By definition, we can say what? We can say 0. We can say capital C is an antiderivative of 0. Okay, capital C is the antiderivative of 0. And since C can be any constant, so any constant is an antiderivative of 0. Now, so let's repeat this exercise. The derivative of x equals to 1. Then we can say x is an antiderivative of 1. All right? And keep going. If we say x derivative of x squared is 2x. And then what can we say? Well, we can say x squared, okay, is an antiderivative of 2x. X squared is an antiderivative of 2x. Now, if we do a little bit, if we do a little bit algebraic manipulation, right, we know that the antiderivative is x squared, right? For 2x, the antiderivative of 2x is x squared. If we multiply both sides by half, right? And by derivative law, we can bring the half inside the derivative, right? Because why is this? Because we have learned derivative of any constant multiplied the function is equals to the constant multiply derivative of f. Right? We have learned this law before. So after this manipulation, what can we say? We can say half of x squared is an antiderivative of what? of x. Okay, so half of x squared is the antiderivative of x. All right, so you can see how we find antiderivative of functions, right? Antiderivative functions. Continue with this process. Continue with this process, and I think you know where we're gonna get this to. We're leading this to what, right? The derivative of x to the power 3 is 3 times x squared. Sorry, 3 times x squared. And then, of course, we can say, like we did before, x raised to the power 3 is an antiderivative, of 3x squared, okay, of 3x squared. And you know what I'm going to do next, right? And then if we divide both sides by 3, so from this form, we're getting, we divide both sides by 3, so this is going to be 1/3. And to apply the same property, so we bring 1/3 inside the derivative. Okay, so 1/3 of x raised to the power 3, this piece is an antiderivative of x squared. Is an antiderivative of x squared. So, okay, you can see we apply this property. Now, how about xn? X sub n. For x sub n, right? So we want to get the antiderivative of power, right? Of power. The derivative of x raised to the power n is n times x raised to the power of n minus 1. Okay, so please derive it with me, okay? Because from this point on, we're going to be using this formula. And of course, we can say xn, right, is an antiderivative of x raised to the power of n minus 1 multiply n in the front, right? That's pretty straightforward. But then if I modify this sentence, okay, if I change this to n plus 1, then this will be n plus 1 multiply x raised to the power n plus 1 minus 1. N plus 1 minus 1, it will be just x raised to the power n. So now we can say x to the power of n plus 1 is an antiderivative of n plus 1, okay, raised to the power of xn. All right? So x to the power of n plus 1 is an antiderivative of n plus 1 times x raised to the power n. That's not a problem. Now, we want to know what is the antiderivative of, okay, what is the antiderivative of x to the power of n? What do we have to do? Okay, so we're going to divide on both sides by n plus 1. Okay, so we're going to divide this on both sides. All right, we don't need the parentheses, and bring this one inside. Bring this one inside. 1 over n plus 1. So now we got the antiderivative of x raised to the power n. So the antiderivative of x raised to the power n is the antiderivative of x raised to the power n. Okay, so now we're formulating, we're making our own table of antiderivatives. Okay, so this is one of the formula. Okay, so the antiderivative of x raised to the power n is 1 over n plus 1 multiply x raised to the power n plus 1. Continue this process. I think we're ready to make a little table, right? So let's make that table. Okay. So we're going to do a little bit summary column. Let's make some rows. Okay. So this is the function, lowercase function, right? The antiderivative of lowercase f. Okay, we can call it capital F if you want, or just leave it like that. Okay, so what do we got? If a function is 0, its antiderivative is constant. If function is 1, its antiderivative would be x. Okay, and for antiderivative of function is 1, its antiderivative is x. If function is x, its antiderivative is half of x squared. Okay, this is actually very commonly used. And how about x squared? The antiderivative of x squared is 1/3 x raised to the power 3. So how do you, I hope by doing this you will not need to memorize these things, because all you have to do to verify if you got the right answer is just take a derivative of antiderivative and you should get the function itself. All right, so how do we check the answer? Right, how do we check the answer? We check the answer that, like we have what we have done by definition. We've done by definition, derivative of constant, right? And the derivative of x equals to 1. So all of these we did earlier, those are the ways to check, right? And over here, we got this. And finally, when the function is x raised to the power of n, its antiderivative is n plus 1 under 1 x raised to the power n plus 1. In fact, all of these formula, okay, so now we just have to put this together, okay, we just leave that out, just put it here, okay. Check by definition. Check by definition. Okay, check by definition. So function is antiderivative, so the antiderivative of x squared is 1/3 x raised to the power 3, and this is how we check. And now this formula works, right? So basically give us the formula, so we don't have to memorize all of these. The formula x of n actually cover all of them, but we need to understand n cannot be -1. N cannot be -1, okay? So we need to note in this case, all right, n cannot be -1. Why n cannot be -1? Well, if n is -1, we're going to get a 0 denominator. Then you say, well, how about, what if what if, right? What if we want to, what if x, what if n equals to 1? I'm sorry, what if n equals to -1? Well, x raised to the power -1, what is that? That is equals to 1 over x. We know, right? The derivative of ln x equals to 1 over x. Okay, so I'm going to bring this forward. Hold on. Sorry. Where did it go? All right. It's coming back. All right. So I'm going to bring these two formulas forward. Okay. To put in the formula table. Okay. All right. We want to explain about these tables. We want to explain about these two cases. This formula, we know it's true, but this is the derivative of ln x without the absolute value. So when this formula applies, we must do it in the domain of x, which is x is greater than 0. So this formula is used when we know if x is positive. The other formula, however, its domain is x is not equals to 0. Okay, so this domain is for x not equals to 0. And of course, we know that derivative is also equal to 1 over x. So which one do we use? Okay, which one do we use? If you know x is positive, then you can use this one. If you're not sure, you just use this one. It's just this one. In fact, this one is commonly used. This one is more commonly used. Okay, so we're going to put it here. So what is the antiderivative of 1 over x? According to definition, right? It's right here. Which this is how we check it. This is how we check it. Therefore, the antiderivative of 1 over x is ln absolute value of x. And this one, of course, it covers the other case. It covers the case when whether x is greater than 0 or not equal. It covers both cases. You know what I want to do? I'm going to make another table because I couldn't keep it this way. All right, so I'm going to, this is the end of this table for now. Okay. And I'm going to put it here. So we're going to make another table to continue, right? Because otherwise, if I move the table, it's going to make it, it's not very convenient. But anyway, so I'm going to put it here. Just add one more row, okay, for our information. Okay, so for general case, right? X is, of course, x cannot be 0. But if we know we got to find antiderivative 1 over x, and if we know x is greater than 0, then the antiderivative is ln x, and of course that can also be verified, which is without the absolute value. Okay, so let's continue to make these tables. All right, so I'm going to, and then in the last, we're going to put them together. Okay, we're going to put them together. Okay, now continue. If we have a sum or differences of functions, then we can take their derivative respectively. So this formula will still be valid for antiderivative. Okay, this formula will still be will be useful for antiderivative. So for now, we're going to just leave it out there, and we will get examples to use it. Okay, the derivative of e to the power x is e to the power x. Okay, so because of this reason, if we have a function e to the power x, and we know that its antiderivative is also e to the power x, no problem. Okay, and how about derivative b to the power x? Derivative b to the power x multiply ln x. I'm sorry, ln b. So we know the antiderivative. We know the antiderivative of b to the power x times ln b is b to the power of x. So of course, if we want to know what is the antiderivative of b to the power x, and we're going to divide, we're going to use the same technique. Okay, so that would be the antiderivative of b to the power x. So b to the power x go there. Its antiderivative is this piece. And this is the reason. And this is the reason. So we know how to check it. And now it comes to the trig functions. Okay, come to the trig functions. The derivative of sine is cosine x, right? So sine x is the antiderivative of cosine x. So cosine x, its antiderivative is sine x. And this is the reason, right? Now, continue, the derivative of cosine x is what? Is negative sine x. Okay, so let me put some more rows. All right. And what is antiderivative of sine x? Right, so we're going to bring this, we're going to subtract, we're going to multiply negative sign on both sides. So the antiderivative of sine x is negative cosine x. And the reason is such. The reason is such. All right, you can see we're applying the definition many times over. What's antiderivative? What's a derivative of tangent? Well, that's a secant square, right? So secant square will be the function. Its antiderivative is tangent x, and that's because this is the reason by definition. Cotangent x. Okay, what's the derivative of cotangent x? All right, the derivative of cotangent x negative cosecant square. All right, so the antiderivative of cosecant squared, if we put a negative sign in front of it, in front of cotangent, so we bring the negative sign over here by multiplying both sides by -1. So we get the antiderivative of cosecant squared is negative cotangent. And by definition, so this is by definition. Derivative of secant. Derivative of secant is secant x multiply tangent x. We know that the antiderivative of secant x times tangent x is really secant x. Right? So what we remembered about derivative can be used to determine what are the antiderivative of these simple functions. So you don't need to have to, memorize a whole bunch of other stuff. Okay, so let me add some more rows. Okay, the derivative of cosecant x is equal to cosecant x. It's negative. Okay, multiply cotangent. By this time, I think these, you don't really need to memorize them, but some of them can be useful. okay? So some of them can be useful. So here, we're going to bring the negative sign on the other side. Okay, so that would be the formula. So the antiderivative of cosecant times tangent is negative cosecant x. Okay. Removing this, we're almost done. We're almost done. Logarithm, right? Logarithm any base. So we shall put these with our first table, with our first table, which is the more general form, right? The more general form. So I'm going to add one more row. Okay, add one more row. So you can see if we talk about antiderivative of any base, right? So if I multiply ln b on both sides, ln b on both sides, then I will get ln b here, right? And bring ln b to, this is not a commonly used. So when you need it, you just know how to derive it yourself. So this piece is also an antiderivative of 1 over x. So this is another form of antiderivative of 1 over x. Okay, what kind of x? Positive. X must be positive. Okay, because we're looking at this function. So in this case will be x greater than 0. Okay, so antiderivative for 1 over x has this form. What's the difference between this form and the other two forms? Well, this form is any base of your choice. Any base of your choice. And of course, the base has to be larger than 0, not equals to 1. Okay, be consistent with what we learned before. And of course, the proof would be this one. The proof will be this one because the derivative of that equals to 1 over x. Okay, ln b is a constant. This is really not very much used at all. But just in case, you know how to derive it. So this is the second table, right? And the last table, I would like to, let's see, how many rows do we need? 1, 2, 3, 6, right? So 6, okay, we got 6 tables. Just one more time. Okay, just one more time. We get to practice with, okay? So this one, by this time, you should be pretty familiar with it, right? The function is right here, and its antiderivative is arc sine. Okay, and the second one, oh, we just delete it. And the second one, right? So I'm going to bring this negative sign to the other side, right? So this will make bracket. So the antiderivative of 1 over x, 1 over root 1 minus x squared, we have another form there, right? And these are the same. So this left-hand side has, the same function has two different antiderivative. Okay, so it's up to you which one you use, right? Which one you use. Tangent, oh, I'm sorry, arctangent, right? So this is the function, and its antiderivative is this arctangent. Okay, so this is the derivative. I'm sorry, hold on, I cut it out. Okay, cotangent, arc cotangent, right? So if I bring this negative sign to the other side, and then we got another antiderivative for 1 over 1 plus x squared. And that is going to be negative of arc cotangent. Rarely used, guys. Okay, I just put it here so you know how to derive it. Okay, the purpose of doing this is not for you to memorize them, it's so that you know how to derive them. And last, and these two are rarely used. Okay, so we got two, right? We got two of these, right? And arc cosecant, arc secant. All right, so this antiderivative, so we're going to bring the negative sign on this side, multiply negative on both sides. So this is negative. These forms, they are antiderivative with two forms, rarely used, but learn how to derive them in case you need it. I think in the process when you're deriving it, you get to learn, you improve your algebraic skill. Now, remember we had a theorem at the beginning, didn't we? We had a theorem, we said, it says if capital F is an antiderivative of lowercase f on an interval I, then the most general antiderivative of f on I would be adding a constant, and constant is anyone. Okay, so in some cases, right, you may be asked for the most general antiderivative. Okay, if you ask that question, what do you do? If you ask for that question, what you need to do, you would just add more constant, the most general antiderivative. So I'm going to make another column. I'm going to make another column right here. Okay, the most general antiderivative. Okay, the most general antiderivative, we're going to put it here. Oops. General, most general form. Most general antiderivative. Oh gosh, I'm sorry. Most general antiderivative. Derivative. Okay, then would be all of these. Each one of them will be adding a constant, and this one adding constant is still constant. No need to do anything more. But this one will be adding a constant, any constant. So you guys got what I meant, right? So sometimes if you're being asked for that, you just add these constants to the general form you got. All right, the same thing for the other forms. Okay, the same would be true for those other forms. So the most general antiderivative, okay, dash. So the most general antiderivative would be all of these, right? Plus constants. So you will find out very soon in the next chapter, you're going to see that these are common practice when you are asked to find antiderivative. You're asked to find antiderivative, okay? All right, so this last table Okay, so since we're doing it, let's just do it anyway. Okay. Most general antiderivative, oops, sorry. Most general antiderivative. In the textbook, you'll find some tables, but I think our table is probably the most comprehensive, okay? We don't have hyperbolic functions listed here. Other than that, we got more than the textbook has listed. But these are not intended for you to memorize, okay? These, you can see I went through this so that you know how to derive it with your prior knowledge about derivative. You can derive all of these all by yourself. You don't have to memorize them, okay? So that's all for this lesson. Thank you for watching.